In today's lecture, we're going to do something that is a little bit controversial. And what we're going to do is we're going to discuss an interesting topic without rigorous definitions. And we're going to use pictures. Up to this point, we have pretty much defined everything in a rigorous way. And even though we use pictures a lot, the pictures are just to motivate an idea or to motivate certain steps in the proof. But the proofs that we have given, they were rigorous proofs written formally, or in some cases where if the proof would have been too long, we have gave an outline of an idea of how one would go about proving the result. We might draw pictures just as a way to, motivate the steps of the argument, but the picture is not part of the proof. So for example, when we talked about copy and paste, for instance, there were a lot of pictures there, but the actual manipulations are being done on symbolic. So you have a symbolic and you're manipulating a symbolic. The only thing we really did not prove, I would say, is the triangulation theorem. So the triangulation theorem we have to skip. It's just too difficult. But today we're going to do something where we're not even going to try to define our terms. We're just going to draw pictures and we're going to think in terms of pictures. This is why I say this is a little bit controversial, because one would say that in a high-level math class, in a pure level math class, things should be done in a formal way. However, my defense would be that this is a one-time topic. This is not something we're going to be using ever again in the remainder of the course. And so because of that, it therefore makes sense to why go through the difficulty of trying to define things that are picture-free when we can at least present a very interesting theorem in topology that nicely connects with things that we've talked about, mention all of that, somewhat prove things if we're willing to use pictures, and then when we move on to different things, we will not need to reference it again. So this is sort of something we're showing because it fits nicely with the previous results that we already have. So first, I want to say what is a graph. Then we'll say what is an embedding. We know what a surface is. So let's say what a graph is. We've never really defined a graph yet. We've drawn pictures of graph, but we never really defined it. But maybe, at least today, we'll define what a graph is. So the picture of a graph is, it's a space that looks something like this. There's vertices and there's like what we call edges. So things like this. Maybe this one goes underneath and so on. So let's say what a graph is. So definition, a graph is a Hausdorff space, let's say X, which contains a finite subset. So let's call this finite subset V, and we call it the vertices. So the vertices is a subset of X. It's a finite subset of X. So in particular, it's a closed subset because this is a Hausdorff space. A finite subset in the Hausdorff space is always a closed subset. Also, V is discrete. That's going to be a discrete set because X is Hausdorff, because any 2 points can be separated. So V will be a discrete subset. So this has the discrete topology. So X contains a finite subset. We call it the vertex set. And there is a collection of subsets. Let's call them E1, E2, En. So there's a collection of subsets so that every EI is homeomorphic with a closed interval. Because topologically speaking, these edges, so you're going to be calling these your edges, every one of these edges topologically is a closed interval. They're homeomorphic to 0, 1. So that every one of these edges is homeomorphic to a closed interval. And the endpoints of EI are in V. Now, what do we mean by an endpoint of a set? We understand what it means to be an endpoint over here, but you have to understand that in topology, this is an abstract space. You cannot necessarily visualize it. So what does it mean for this to be an endpoint? Well, I think this is perhaps the easiest way of describing to be an endpoint. You could say that there's a homeomorphism from here to here. And when you have the homeomorphism, 0 and 1 are just the corresponding points here. But I think even easier without using a homeomorphism, you can just notice that in this closed interval, if you remove the left endpoint, and when you remove the right endpoint out of the space stays connected. But if you remove a point somewhere inside the interval, so here's your interval. So notice that if you remove 0 or if you remove 1, the space stays connected. But if you remove an interior point, then you disconnect the space into two pieces. So therefore, what I would say is I would just define an endpoint of something like this to be the 2 points that you can remove without disconnecting the set. So those are called the endpoints of EI. I prefer to do it like this by removing points, because then you do not even have to use a homeomorphism. So the endpoints of EI are contained in V. So as you can see in this picture, these are the edges. Their endpoints are elements of the vertex set. And furthermore, so these subsets are called edges. So these are called the edges of the graph. And furthermore, if you do EI intersect EJ, this is either empty or is a vertex. They intersect in a vertex. So as you can see in this particular picture, if you draw, let's say, these two edges, this edge and this edge do not intersect, these two edges do intersect, and they intersect in one vertex, right? They intersect in a single vertex. So that is what we call a graph. Okay, so these are the endpoints, and furthermore, they intersect in the empty set, or it could be a vertex. So that's the definition of a graph. This is, I guess you can call this a topological graph. It's a little bit different from what is known as a combinatorial graph. A combinatorial graph, instead, if you've seen the definition, it consists of a vertex set, and then it consists of a collection of subsets of the vertex set, 2-element subsets of the vertex set. And then you call that a combinatorial graph. So when you take, for instance, like a combinatorics course, that's probably the way they define a graph. And you do that in a combinatorics course because in a combinatorics course, you're not really interested about the points on this edge. Like you would not say, like for example, in like computer science, when you talk about graphs, you talk about the nodes, and this is some kind of network, and the lines, they just represent the connections. You're not really interested in the points that are on those lines. You're only interested in the endpoints. The lines are only drawn to indicate the connections, the relationships that exist between the vertices. But in topology, you actually do care about those points as well. So I think maybe more appropriately, it should be called a topological graph as opposed to a combinatorial graph. But of course, they're both very similar, that a topological graph can be given a combinatorial structure because every single one of these edges ends up defining a relationship on the vertex set. And then you can recover the combinatorial graph. But the difference is that here in topology, you are also interested on points on the graph as well. So a topological graph will contain an infinite number of points because these are also points of your space. So that's like the small distinction. So this is the definition of a graph. Now, to make comments, there are some people that would, let's say you have something like this. Now, if this is E1 and this is E2, then the intersection is now going to be two vertices. Let's say V1 and V2. So this is V1, this is V2, and this is not allowed. This is not allowed. So our definition does not allow it. Why not? Well, because we're trying to keep the definition simple. You could allow it if you want. You could, but if you allow something like this, then you have to slightly change your definitions. I guess the way you can you change your definition is then you would say that EI intersect EJ is then a subset of the vertex set, as opposed to being either empty or a single point. You then would have to say it's some subset of the vertex set, because then you allow things like that to happen. Or, for example, yeah, something like this. So people would call this, so some people would call this a multigraph. when you have multiple edges between the vertices. Sometimes you have this, sometimes you have this. So you can just keep on doing it, right? You can kind of keep on doing this as many times as you want. Usually these graphs do not come up in combinatorics for a simple reason, because as we indicated, the graph is supposed to represent a relationship between two vertices. So why would you draw an edge to represent the relationship and then draw another edge to represent the same relationship? But in topology, you might imagine why you want to do something like this. It sort of generalizes it. So if you want, you can include that in the definition. Everything would be fine. And another thing that you can do is you can also include loops. So there's some people who would do this. So that you can say this is, so is this, I mean, would you say this is a graph? Well, in topology, you can allow this to be a graph. But then you see the issue is this is technically not an interval anymore. You see, that's the issue. It's not an interval anymore. It's a circle. So then you would have to change your definition and say it consists of edges, right? So the edges are the ones that are homeomorphic to the interval, or it consists of loops. It consists of circles, something that's homeomorphic to a circle. So you can do that, but then you have to slightly change your definition. So if you want to, you can do that. So all of our results today, and again, this is not something you typically do in a combinatorics class. You're not going to say something is related to itself, usually interested in it being related to other things. But in topology, you can allow things like that. So if you want, so if you wish, you can generalize the results of today's lecture to multigraphs. So this is the one that can have multiple edges with loops. So you can have like a self edge, like the one that returns back to itself. So you can do that. So this is what we call a graph. So you can either use the definition that we gave at first, or you can think of this more general type of a graph. And so this is a graph. And then we also talk about this thing called embedding. So what is an embedding? So let's say what this is. So we say X embeds into another space Y if and only if there is a map which maps X homeomorphically onto a subset of Y. So it's a homeomorphism of X into a subset of Y. So it's not a homeomorphism with Y, it's a homeomorphism into a subset of Y. So to use a very simple example, R embeds into R2. Like, you want to say that R is a subset of R2, that's what you want to say. And you can say that, and this is somewhat sloppy, but sometimes mathematicians write that, because as you know, mathematicians like to be sloppy. Technically, R is not a subset of R2, because this consists of real numbers, this consists of pairs of real numbers, so technically this is not correct. But what people mean is there's a map from R to R2, and it can be like this. Let's say f of x is equal to x comma 0. That's one way to do it. And then you are embedding the real line in the real plane by mapping it to that subset. Right? So you can see that this subset is basically like this. They look exactly the same. But technically, this is not a subset of that because this consists of pairs. So then you're saying there's an embedding. There's a way that you can see that space in some larger space. So that's what we mean by an embedding. There's a way to put the space into another space. This one is used quite a lot, and this is the embedding of R2 in S3. You actually had something like this on the homework. The idea is that this is the sphere, this is the North Pole, right? This is the North Pole. Here you have your plane. So your plane represents R2. And now what you notice is if you pick a point in R2 and you draw a line from the North Pole to that point, it intersects it somewhere in the sphere. And that defines a mapping. So that is a mapping. That is a mapping from R2 into S3. So every point will get mapped somewhere except for the origin. So what would happen is then R2 will be mapped to the sphere minus the North Pole. North Pole. So that would be the one point which is missing. But because you can see that as, like, I mean, you can see that, so you have this point and you have this point. The closer this point gets to the North Pole, when you draw this line, it goes further and further and further out. So as this point moves closer to the North Pole, this point blows out to infinity, right? So that would be the one exception. So you have a one-to-one correspondence between R2 and every point of S3 other than the North Pole. So there's a way to embed R2 into the sphere. Oh, I'm sorry about that. I wrote S3. Sorry about that. I meant to say S2, of course. S2. Okay, so we have this is an example of embedding. And the question we're going to ask is this. Well, first I want to just state this fact. So it can be shown that if X is a graph, then it can be embedded in R3. You can always embed a graph in R3. So what does this mean? This means that, so more concretely, you can draw a subset of R3 which is homeomorphic to X. Okay, so X is a topological space. So it could be something that is very abstract, something you cannot see. But when we say that the graph can be embedded into R3, that means you can draw a picture in R3, which is a concrete Euclidean visualization of your abstract topological graph. This is not difficult to prove. So this is not difficult to prove. You can even do it using straight lines. So you can make this subset of R3 be a union of straight lines, straight line segments. It's not exactly the most important result. I'm thinking maybe, possibly, I'll put it on the homework, possibly, if I think it's interesting enough, if it fits with the exercises. So this is just a general fact about graphs. Graphs can always be embedded in R3. Actually, while we're talking about embeddings, every compact connected surface can be embedded in R5. This is a little bit more difficult to prove, but it's also not that difficult. It's not that difficult. It's like you would think this is some kind of important result, but it's not exactly an important result in topology. It's just interesting, but it's not exactly important. It's not, as far as I know, it's not really used anywhere. Some surfaces, however, let's just say this, however, some surfaces, for example, P2, cannot be embedded in R3. This is actually more interesting. So this means that it's not possible to draw a Euclidean visualization of the projective plane. So you can only describe it as an abstract space. Now what you can do is you can do something called immersion. So there's something called an embedding, and there's something else called an immersion, which we're not going to define because we do not really need to know what that is. But an immersion is close to an embedding. It's what the pictures that we drew of P2, if you've noticed, they pretty much almost are perfect, except there's these few points where it has to cross over itself. So that's like as close as we can get to an actual embedding. And this is difficult. So this one's also, if you're interested, this one is also not difficult to prove. It's harder to prove, but it's somewhat of the same proof. It's just more steps that are involved. But this one, surprisingly, this is very difficult. This is very difficult to show. I am not familiar with any simple way of showing this. I think there's, I think what Hatcher does, so probably heard of this book called Algebraic Topology by Alan Hatcher, which is actually not a good book for a first-time reading. It is definitely not a very good book. When I was in graduate school, I had a classmate who had Alan Hatcher as his professor for topology. So he told me that as a professor, Alan Hatcher was a fantastic professor. He was a very, very good professor. He would motivate. His classes were excellent. But his book was not, it's very hard to get things out of his book. His book is more appropriate for a second reading. Like when you already know it and you read it a second time, it's more appropriate for that. He has a tendency in his book to leave out a lot of steps. He has a tendency also to, some of his proofs are, they're not rigorously written. He might draw some pictures and he would move on. And his goal is to provide you the insight that makes the proof work, but to actually write the proof, you have to write it yourself. So for learning it for your first time, it's actually not a good book. People who already know algebraic topology well, they like the book because they say that Hatcher is able to take some complex abstract idea and present it in a more intuitive way. The problem is that what is intuitive for one person might not be intuitive for someone else. For someone who's learning it for the first time, they need to see things written out more rigorously. So there's a lot of hidden arguments in the book. So it's not really the best book for learning algebraic topology. But it also happens to be a very advanced book. He does things in that book that are more advanced than other books. For example, he actually talks about higher homotopy groups. Most books on topology do not talk about it, but he does. So, and I believe what Hatcher does, if I recall, he uses something called Poincare duality to justify this. But that's a complicated result. So it's, yeah, I'm not sure of a simple way to justify this, but this one's more interesting and difficult to prove. So this is what we call embeddings. So every graph can be embedded in R3. So let's say this about graphs. Now, well, before I do that, so you see, sometimes surfaces can be drawn in R5, the orientable ones, and the non-orientable ones cannot be embedded in R3. And the same thing actually happens with graphs. Some graphs can be embedded in R2, and some graphs cannot be embedded in R2. So every graph can be embedded in R3. So you can always do it in three-dimensional space, but you cannot necessarily do it in two-dimensional space. So some graphs can be embedded in R2, but not all of them. So the classic example, so this is the classic example. This is the K33 graph. So so what's the K33 graph? So you have, so the vertex set, can be written as, let's say, V1 union V2, where each of these has 3 vertices. So there's 3 in this one, and there's 3 in this one. So that's why you write it. And the K means it's complete. There's an edge between each one. And for each V in V1, and let's say W in V2, there is an edge, E, whose endpoints are V1, are V, and W. So this is called a bipartite. So partite stands for a partition, because you break it into two disjoint pieces. So this is a disjoint union. So maybe I should write it like this. I should use the disjoint union symbol. V is a disjoint union of these two. So you have a disjoint collection of vertices. And for every vertex here and every vertex there, there is an edge in your graph, right? So a graph consists of edges. So X is a space. I think that I might have forgotten to mention this, but I think this part is obvious. I think I forgot to say this. I think I forgot to say that in a graph, so if X is your graph, your topological graph, and E1 and E2 and En are your edges, then the graph is the union of its edges. I think that part should be obvious, even though I forgot to mention. I'm pretty sure I forgot to mention that. But that part should be clear. So a graph is a union of its edges. And if you look at the edge set that makes up the graph, every edge set, the endpoints are between those two. And conversely, any vertex here and any vertex there, there is an edge, right? There is exactly one edge. I'm not going to write it here because in our definition, we do not have multigraphs. So it's understood, but there's exactly one edge. So the picture is that you have three vertices. And maybe the way you want to draw it is you do it with colors. So you have three vertices of the red color, and then you have three vertices of the blue color. So that's why you call it a bipartite graph, because you have partitioned the vertex set into two separate colors. So the colors are just labels. And then you're saying that for every vertex of one type and for every vertex of the other type, there is an edge that connects them together. So there's an edge. So there's going to be an edge going like this. There's an edge going like this. There's an edge going like this. And then there's an edge. Now, here's something you can do. You are permitted, when you're drawing graphs, to go like this. Okay? The points of intersection, they're not part of the space. And if you want to be perhaps more accurate, you can draw the edge as going underneath it. Right? It goes underneath it because that's what we mean that every graph can be embedded in R3. So you just go underneath it, right? You can go underneath it. And for this one, you can go underneath it, just going underneath it, because in three-dimensional space, you have that extra dimension to move along. And then you have this. And then for this one, you go underneath those two. And, well, you can probably just do this, and then you do this, okay? So you can clearly see that this graph can be embedded in three-dimensional space by just taking these edges and moving them underneath. They do not have to be straight lines. But it is possible, by the way, to configure these points in the space in such a way so that the straight lines between them will also not intersect. It's not particularly that difficult to prove. It's not really important. It's just an interesting comment or observation. But you can ask, can you do this in two-dimensional space? Now, this is also something that's called the three utilities graph. So it's called the three utilities graph is because you think of these as the utilities. You think of this one as being gas, water, electricity, and you want to connect those three utilities to three houses. So this is house 1, this is house 2, house 3. And the three utilities problem says, is there a way to connect the utilities to the houses without crossing them over? So of course, you try doing this. Well, you cannot go like this, so you have to change your path. You can go like this, and here you can. Well, no, you cannot do that, but I guess you can do this, right? Then you have to connect this one to this one. Well, you could connect this one, and you could also connect that one, but then how do you go from that one to the other one? So it seems there's no way to do it. It seems that if you try going like this, there's no way to go like that. There's no way to kind of go around. So it seems it's not like it seems the only way you can do it is if you cheat and you go underneath it, right? Then you have to go underneath it to avoid crossing them over. You see, you're not allowed to cross them over in the plane, because if they cross in the plane, right, if you draw them like this in the plane, then you're violating the condition for a graph. The condition for a graph says that if you have two edges, then the two edges intersect in their vertices. So these are not, if this is not a vertex, then it's not supposed to intersect there, because that's not, I mean, you're violating the definition of a graph. Now, a lot of times when we draw graphs, the reason why it's okay to draw it like this is because graphs can always be embedded in three-dimensional space. So we then just interpret this as going underneath it or above it, or maybe going underneath and then above. It does not really matter, but you can draw it in the way so that they're not crossing over each other. And then you've embedded the graph in three-dimensional space, so you can do that. But can you embed it in two-dimensional space? That's the question. So here's like another famous graph. K5 can be embedded in the plane. So you have 4 vertices, and between any 2 vertices, you're going to have an edge. Now, at first you would say there's no way to do it because now you're crossing over each other, right? You're crossing over, but then you do not have to use a straight line. You can just do this. And you've just embedded, you see, this is a Euclidean representation of this abstract topological graph. So that's what we talk about graph embeddings. So K4 can be embedded, but it's a well-known theorem. This is the other classic one. K5 cannot. You cannot embed K5 to the plane. You can embed it in space, of course, but you cannot embed it into the plane. So let's make a definition. Let X be a graph. We say X is planar. It's a planar graph if and only if X embeds into R2. It can be embedded into the plane, hence the name planar for plane. So it's a planar graph. So the claim is that K33 and K5 are not planar. They are not planar graphs. They cannot be embedded into the plane. So this is like a well-known result in graph theory. In fact, the other interesting thing about this is that there is something called the Kuratowski theorem. That says that these are basically the only exceptions. So, I mean, I'm not going to say what that means basically, but the Kuratowski theorem says that these are not planar. Well, that's actually not part of the theorem, but before I say what the theorem is, so these are not planar, and if a graph contains this one or that one as a subgraph, so if you can find a graph sitting inside X, which is either this one or this one, then that means the larger graph is also not planar, because if you can embed X into the plane, then that subgraph of X will also embed into the plane. So that should be pretty clear. So if a graph contains this one or this one as a subgraph, then the graph cannot be planar. So for example, K5 is a subgraph of K6, because K6 it's the graph, it's the complete graph on 6 vertices. But if you have 6 vertices, you have 5 vertices, and you include all of the edges of those 5 and something more. So because K6 contains K5 as a subgraph, it means that K6 is also not planar. So obviously, if a graph contains either this one or this one, it's not planar. And basically what the Kuratowski theorem says, it says something very surprising, and it's essentially the converse of the statement. And it says that if is not planar, then it has either this one or that one as a subgraph. That's basically what it says, without getting to the details. So that's the really surprising theorem, that those are really the only exceptions. So we're going to prove this result. Our proof will be a little bit suspicious. It's going to use some visual stuff, but it'll be pretty convincing in the end. Yeah, in the end, it'll be pretty convincing anyway. Now, last time we talked about Euler's formula. And there's Euler's formula for planar graphs. For planar graphs. So here's what it says. So if x is a planar graph, let v be the number of vertices of x, e be the number of edges of x, and f, this is the number of faces of x in its embedding. It's the number of faces. So vertex and an edge, we know what that means, because a graph, by definition, consists of a vertex set. That's a finite subset of points for the graph that are in X. And it consists of these things called edges, subsets that are homeomorphic to intervals, whose endpoints are the vertices and which intersect exactly at the vertices. So anytime we have a graph, we know what the vertex set is, we know what the edge set is, so we can just calculate what those numbers are. This is part of the graph. The f, this is the one that comes from the embedding. Okay, so this one, so this quantity is the one that comes from the embedding. So you embed the graph in the plane, and after you embed the graph in the plane, it determines the number of faces. So it's similar to what we said last time when you talk about triangulation and you talk about faces as the number of triangles. And also, it's similar to when we talked about Euler's formula for polyhedron, that when you have a polyhedron, the faces, those are the faces that bound the polyhedral solid. So those are the planes that bound it. So f is not actually part of the graph. You embed the graph in the plane, and after you embed the graph in the plane and you visualize the way the graph looks like, you can count how many faces it has. And Euler's formula for planar graph says that if you take vertices minus edges plus faces, you get something surprising, that it's again equal to this number 2, this mysterious number 2 that we've seen before. And it, like, you would think that there has to be a relationship between this formula and the previous formula. Last time we talked about Euler's formula for polyhedron, but this is Euler's formula for graphs. Because they look so similar, you would think there has to be a relationship between the two formulas, and there is, and we'll explain it. But first, I want to show you an example. So let's look at this example. So we go back to this graph K4. And this is the way you can embed this graph in the plane. You're going to draw this. And instead of drawing that, which you're not allowed to do, and you're not allowed to go underneath, because it has to embed in the plane. You can only stay in the plane. You simply draw this one. And now you draw your faces. So this is a face, okay? This is another face. Right? These are like the regions that are being created. This is another one. This is another one. This is another region. And let's check the formula. So in this graph, the number of vertices is 4. Right? Number of vertices is 4. The number of edges. Now you can count the edges 1, 2, 3, 4, 5, 6. But there's a shortcut if you've never seen it before. This is 4 choose 2. Because you have 4 vertices, and you're choosing 2 of them, because between any 2 there's a edge. So it's 4 choose 2, which is 6. And the number of faces is equal to, so we go ahead and count 1, 2, 3, and we get 3. And let's go ahead and count what this is. So then we have 4 minus 6 plus 3. Is this equal to 2? Let's check. It's supposed to be equal to 2. So we have 4 plus 3 is 7 minus 6, and we get 1 is equal to 2. And that is not true. Something does not work out. What went wrong? Well, what actually, so everything is correct. This formula is correct. The statement is correct. So what actually went wrong? So there is something that's very surprising, that this is not what you would think. And there is an extra face that is not being included. And it's this. It's the face on the outside. You can call this the outside face. Now that is very confusing. Like, why would you do that? But we'll explain why you have to do that. I mean, clearly you have to do that, otherwise the formula does not work. But that's not very satisfying. So this number would be 4, this would be 4, and then you have 8 plus 8 minus 6, so that would be 2, and then 2 is equal to 2, and everything works out. So when you're using Euler's formula for planar graphs, you also have to count the outside face. Okay, so now let's explain why this formula is correct by relating it to our previous discussion from last class. And you will see a nice explanation where the 2 comes from and why you have to include the outside face. So here's the key observation. So here's like the key observation. So if x embeds into R2, then x embeds into S2. So what's the difference between R2 and S2? The main difference between them is one is compact and one is not. So this is a surface, but this one is a compact surface. And in topology, we like to work with compact spaces because they just work better. They just behave better. So if you have an embedding into R2, then you have an embedding into S2. And this is just a picture we drew before, that you draw your sphere, you draw your North Pole, you draw the plane, right? You go ahead and you draw your plane, and then that's passing through the equator. And then for every point in the plane, if you connect them, it intersects somewhere. And so every point in the plane can be mapped to a point on the sphere. So this is an embedding. There's a way to embed. This is a one-to-one correspondence. So there's a way to map R2 into S2. So you can embed this one into this one. And so you can visualize your graph on the sphere. Okay. So now look at what happens. So let's draw our graph, but this time as a graph on the sphere. So here's the sphere. And let's draw our graph. Let's draw the graph. Maybe to make the picture simpler, let's just draw K3. Or maybe, how about I try drawing K4? Let's see if it goes well. If it's too hard to draw, I'll go back down to K3. So we have 4 vertices. Does not matter really where you draw them. And then you have this piece. You have this one. You have this one. You have this one. You have the one going in front. And now to connect this one with that one, what we'll do is we'll go around from the back like this. We'll go around from the back. We'll go around from behind the sphere, and then we connect them. So that would be an embedding of K4 on a sphere, right? So you've just embedded K4 on a sphere. Can we count now how many faces we get? So we get the face that this is 1, this is 2, and then the other ones are hard to see. Yeah, the other ones are hard to see. I guess. Yeah, so this would be 1, this one right here. This would be 2. So those 2 are easy to see. I guess the next one, it would be this. It would be bounded by this, and it's this piece, I guess. Yeah, I guess it would be that piece. And then you have one more piece over here, right? You have one more piece. So you have your faces. And that explains, by the way, why you need to include that extra face. Because when you draw this graph in the plane, like this, and you start counting your faces, you have 1, 2, 3. But then the outside, you see, this is sort of the outside remaining face. There's an extra face on the sphere. This is the one that kind of goes out to infinity, right? That's the one that's unbounded, that goes out to infinity. But when you embed it on the sphere, that would be another one that has to be counted for. And that kind of explains why you need one more. So when you look at it as a graph in the plane, it's unclear why you have to include that one. But when you look at it as a graph sitting inside a sphere, then suddenly it becomes clear why that is another face. Okay, so What's the explanation? So that's the key observation. And then furthermore, if X is a graph sitting inside S2, then X gives a triangulation for S2. It's giving you a triangulation. Well, almost. Because technically the definition of a triangulation is that we want to make sure that everything looks like a triangle. But if it's not a triangle, so we've made this comment before. You would not call this a triangulation, but you could make it a triangulation by taking this quadrilateral and cutting it up one more time. So you have to introduce one extra edge. And now you have triangles. Notice that it was not a triangulation, and you had to increase the edge by 1. But when you increase the edge by 1, you've increased the number of faces by 1. And so what happens is, if it's not exactly a triangulation, and it consists of squares or pentagons and things like that, you can cut them up further into triangles if you want to, but then the amount of edges that you introduce is then equal to the amount of new faces that you gain. And so the Euler characteristic in the end does not change. So it's almost a triangulation. So therefore, thus, the number of vertices minus edges plus faces, this is a triangulation, and you're just counting how much of each type you have in the triangulation. That has to give you the Euler characteristic of S2. The Euler characteristic of a surface, of a compact surface, that is a topological invariant. It does not matter what triangulation you use, and in the end, it's always going to be the Euler characteristic of the sphere, and the Euler characteristic of the sphere is 2. And that explains where this comes from. So it's actually very similar to what we were saying before, that when you have a polyhedron gives you a triangulation for S2 because it's homeomorphic to S2. And this is somewhat very similar. In fact, what you could do, by the way, if you do not like to draw these embedded graphs, you can go back to the picture of the sphere again. And when you draw your embedded graph like this or something, you can well, no, I'm not going to do it. I think it's just going to make it. I think it's just going to make it more complicated. So let's just forget that I was trying to say anything about that. I realize it's not going to add any valuable insight, and then the pictures, I'm not going to be able to draw the picture. So let's not even go there. The most important thing is that when you embed a graph inside S2, so when you embed that graph, you're getting a triangulation for S2. And so the Euler characteristic has to be 2. This is the Euler characteristic for the triangulation, and it has to be equal to 2. And that explains where this 2 comes from. Now, what's interesting is one can talk about, so we can generalize the problem of graph embeddings and consider embedding a graph in a different surface. So embedding the graph in the plane is equivalent to embedding the graph in the sphere. But we know there's many different kinds of surfaces. So let's talk about embedding a graph in a different type of surface. So for instance, we can talk about embeddings in a torus. Right? So let's talk about embeddings in the torus. So let's make the following observation, that K33 cannot be embedded in the sphere. So we're going to prove this later, to be proved. We will actually prove this later. So K33 cannot be embedded in S2, but it could be embedded in the torus, in the two-dimensional torus. That's all what that does not mean 2 copies of the torus. That's just a two-dimensional torus. Maybe I'll just write it like this: can be embedded in a torus. So you can embed it inside a torus. Let me see if I can find a picture for you. So just give me a moment to find a picture online, because, well, you know what? Maybe I should try drawing it. How about I try drawing it? And if I can draw it, that'll be impressive. And if I cannot draw it, I'm just going to cheat. And I'm going to use something off the internet. Okay, so that is going to be our torus. So we'll have 3 houses, and we have 3 utilities. And I'm not sure if I can draw it, because sometimes I practice drawing something first before I make a video presentation on it. So I'm not sure if this is going to go well. So let's see if we can draw this. So we have something going like this, okay? Now we want to get from this one to this one. So maybe try going like this. Okay, so that's okay. How do we get to that one? Maybe we go like this. Well, that was, I mean, that's not wrong, but let me start again. We're going to connect this one with this one. Then we're going to connect this one to this one. So here's how we can connect it. We can kind of go like this, and it kind of comes around, right? Because it can kind of, you see there's this side which is hidden from us, and then it kind of goes around, kind of comes up like this, and you see it. And of course, if you can do this, then you can also do something very similar, right? There's room to go here. So you would go like this. And then you just come around on the top, which is visible, and then you see it. Then we want to get from this one to this one. So it seems we cannot go down because we have to cross over these. And then I'm thinking, can we go around like this? I'm not sure. I think we crash, right? I think we're going to crash. So let's try going like this. And for this one, we can kind of use the same path, but it's just a small little detour. Like that. And how do we get to the other one? So I'm thinking maybe that was a mistake. Maybe I should have not done that. Maybe I should have went like this. Maybe I should have went like this. Okay, and then I go around like that. Okay, so now they have been connected, and now we have to get from that one to that one. How do we do that? So, okay, I see how to do it, but it's hard to draw. Well, actually, that was a mistake. Okay, let's try that again. I have to go. You see, previously I went around it, but I have to go underneath it, right? I have to go underneath it to that one. And then here I go like this. I continue from the end like that. But then the problem is, it seems I cannot reach that vertex. Yeah, so it looks like I'm not able to draw this. Not able to draw this because oh, I see what the problem is. For some strange reason, I drew this one again. Yeah. So maybe I could draw it. Let me try one more time. Yeah, I was not supposed to draw the edge from here to here because I already drew one. So let's say we go like that. Yeah, but then that's not good. Let's try maybe going maybe this. Let's try going over it. Then try going underneath it. Okay, I see how to do it now. Yeah, so we've drawn an edge from this one to this one. We drew an edge from this one to this one. And we drew an edge from this one to this one. Well, not yet, not yet. Yeah, it seems the moment I draw the edge between these two, then I kind of close it off, and then I'm not able to do this. So as you can see, I'm not able to draw a three-dimensional visualization of this on the spot. So I'm going to cheat, and I'll find the picture online. So give me a moment. So here is an image for the utility graph. And this is the image that they give. You have A, B, C, X, Y, Z, and then you have these edges. You can check they connect. Then you have the blue edges. And you can see you are taking advantage that it's a torus because you are moving around the rings, and then one of them is moving around from the back, something you cannot do on a sphere. You're taking advantage of that hole to move around. And then you can see you can actually embed that object in the torus. So that would be the way you would do it. Now, a better, an easier way of drawing a picture is, instead of using this actual picture of a torus, the way you can draw it is you would draw this rectangle and you would draw your 3 points. So you go ahead and you draw your 3 points. And we understand that the left edge and the right edge, the left and right edge, are being identified together, and the upper and lower edges are being identified together. So let's start drawing. So we would draw this, we would draw this, and we would draw that. And then we have to draw one from there. So we can maybe go like this. And actually, I have an idea. How about we do this? Instead of going around like this, let's do it like this. Let's go up and continue it like this. We're allowed to do that because these two are identified on this polygonal representation for a torus. And then we can go up like this, and these get connected. And then let's go like this, and these get connected. Okay, and now we need to draw something from here to here. So we can draw it maybe like, this. And we can draw this one like this. But how do we get from that one to that one? So it seems you kind of want to go around like this, but this one is getting in the way. So let me change it a little bit. I'm going to get rid of this one. And I'm going to make it go, well, I cannot make it go like that, but I could make it go like this and then continue it down there. I'm allowed to do that, right? So now I've connected it. And now to get from this one, so let's see, we have one going like this, we have one going like this. So we have to, the last remaining one is to get from that one to that one. How do we do it? Well, we go up and then we continue it from there. Okay, and this is like an easier way to draw this. And you have just created an embedding of the graph in your torus. So there it is. That's the 3 utilities graph embedded in your torus. So let's see if we can count. So let's count the number of edges. So the number of edges is going to be 6. No, sorry about that. The number of vertices is going to be 6. So that should be clear. 1, 2, 3, 4, 5, 6. Now the number of edges, there's a shortcut. The number of edges is going to be 3 times 3, which is 9, because there's an edge between every vertex and every other vertex. So 3 times 3. There's going to be 9 edges. Let's count how many faces we have. So it's not as many as you think. You would think you'd have a lot, but it's not as many as you think. So Let me start with this one. So you see, so it's the regions that you're creating. So this entire region over here, right? This entire region over there, that would be one face. That's just one face. Then what else do we have? You see, we have this region. It kind of goes up like this. So this will be region 2. So this is region 2, but it extends from here from the bottom. So this is still region 2, right? It kind of continues from the bottom, and then it continues over. It spills over on this side, so that would still be region 2. Right, and this, well, this is just a continuation of the region, so I'll just put the number 2 over here. So all of this is just part of one big giant region. So this kind of goes up, this kind of extends to the side, and there's actually, you see the 2. It's even more than that. This 2, like it spills over down here, so this would also be 2. Okay, and this 2 continues in here. You see this 2? It continues in here, so this would still be region 2. And then the 2 continues up, so this piece is also part of 2. So that is one big giant region. Like you actually thought, like at first you would think you have a lot more regions, but then you realize it's actually not as many. Now, by the way, this one is just a continuation of region 1, right? So that's your face. That would be your face. And so this is the one that's left over, right? This is the one that's left over. This would be region 3, and this region 3, it continues down here, so that's still region 3. So how many regions do we have? That's what we call faces. That would be 3. So let's see. Vertices minus edges plus faces. So this would be 6 minus 9 plus 3. That's equal to 0. Well, that's surprising. Why is that equal to 0? Why is that not equal to 2? Well, it's equal to 2 when you're embedding it in a sphere, because a sphere's Euler characteristic is equal to 2. A torus, its Euler characteristic is 0, if you recall. The Euler characteristic of a torus is 0. And this makes sense, right? You can see that by embedding it, the number of faces you get is 3, and that's correct. It's equal to the Euler characteristic, which is supposed to be 0, right? This is equal to the Euler characteristic of the torus. So that is correct. So let's call this the generalized Euler's formula. And it says this: if X embeds into a compact connected surface called the surface S, then the number of vertices minus the number of edges plus the number of faces is equal to the Euler characteristic of S. So if it's a sphere, it's equal to 2. If it's a torus, it's going to be equal to 0. If it is if it's 2 tori, if it goes like this, if it's 2 tori, then the Euler characteristic is -2. That would be -2. If it's a projective plane, now that would be kind of unusual to embed a graph in a projective plane because you cannot visualize it. But I mean, you can still talk about embedding it into the projective plane. You can still do that. So if you're embedding it into a projective plane, then the Euler characteristic would be 2. If you're embedding it into a Klein bottle, the Euler characteristic would be 1, okay, and things like that. So yeah, so this is what we have. So X embeds into a compact connected surface S, then this is what we have. And this just follows, I mean, there's nothing to prove here. This just follows from all of the previous results that we talked about. Because if X embeds into S, the embedding gives you the triangulation. So this is the Euler characteristic of the triangulation, and that's a topological invariant, so that's just equal to the Euler characteristic of the surface. So there's nothing to prove. So this is perhaps the nicest proof of Euler's formula for planar graphs, because not only does it give you a deep understanding of where that formula comes from, not only does it explain to you why you have to include that region on the outside, that mysterious region on the outside, it also generalizes, not only does it explain where the number 2 comes from, it also generalizes it to more general types of surfaces. So now what I would like to prove to you is I would like to prove to you that K5 does not embed on, okay, so let me just show you, this is going to be an exercise. So the exercise is to show that K7, actually K8 K8 does not embed into a torus. So K8 does not embed into a torus. Okay, so K5, K6, and K7 all embed. Now, how do you prove it? Well, the way you prove it is you have to just draw a picture. I'm not going to ask you to do it because these are really big graphs. It would be very tedious to try to figure this out. So this graph will contain, how many edges will this contain? 7, choose 2. That will contain 21 edges. That's quite a lot. So, but I'm sure you can find pictures online. I imagine, possibly. I mean, unless it's too complicated, then maybe you will not find it. I imagine the torus is a very popular shape, so maybe you can find it. But if you start talking about a 2 tori and things like that, then maybe, possibly, you would not see some kind of maybe if it's a 2 tori, maybe you cannot find pictures for those, because a 2 tori is not as popular as a simple torus. Because a torus is a very interesting shape, but then the 2 torus is sort of like the same shape, just repeated twice, so it's not as interesting anymore. So I imagine you can find pictures, but you're going to prove this. Now, how do you prove this? So here's what we'll do. So we will give a proof. So we will give a proof that K5 does not embed into S2. And then you modify this proof for a torus. So the proof that we're going to give why K5 does not embed into the sphere, it's a generalizable type of argument. That's the type of argument that you can also do for other types of graphs. So to prove this, we need a result that if you've seen anything about graphs, you've definitely seen this before. This is a very common result. So let's make a definition. So if V is something in the vertex set, maybe I should just, if we pick a point in the vertex set, we define the degree of P as the number of edges. This is in the edge set, which contain P. So for example, when you have a graph like this or something, then if this is P, then the degree would be 2. That would be these two, that would be 2. Oh, warning. I just realized this. I should have said this earlier, but I just realized this. We are assuming our graphs are connected. So in the statement of our theorems and all of that, we're going to assume our graphs are connected. So just a small warning. Okay, so we have this. So the degree would be 2, and then the degree of this one would be 1. There's only one edge that contains it. The degree of this one would be 3. That's the degree. And then there's this very famous result in graph theory, which has a very funny name to it. It's called the handshaking lemma. And the proof will be explained through a handshaking analogy. That's why it's called like this. So it says that if you take the sum of the degree of every point in the vertex set, then that is equal to 2 times the number of edges. It's twice the number of edges. That's called the handshaking lemma. And the reason is quite simple, because let's say you have 2 people, person 1 and person 2. This person, how many hands did this person shake? So these 2 people shake hands. So this person shook his hand, and this person shook his hand. So in total, you had how many total handshakes took place? 2. But there is an edge connecting them because the edge just represents a relationship between 2 people that shook hands with each other. So you have one edge, but the total number of handshakes was twice as much because for every connection, you're counting it in both ways. So that is really that's basically the proof right there, right? If you think of, so if you have a bunch of vertices and then you have connections between some of them, let's say like this, let's say something like this. So this represents this person only shook that person's hand. This person shook both of these people's hands. This person shook, well, this person shook everyone's hand, okay? So shaking someone's hand is a mutual relationship. It goes both ways. So when you count how many so when you're counting this edge, so when you're counting how many hands this person shook, and then you're counting how many times this person shook a hand, this edge is being double counted because it goes this way and that way. So that's why this is the total number of handshakes, and it's twice the number of edges that you have. That's called the handshaking lemma. It's very simple, but it's very powerful, and it is used a lot. And there's something similar, something similar to, this is the handshaking lemma for embedded graphs. So it's basically the exact same lemma, but it goes like this, that if you pick a face from the set of faces, so if you have an embedded graph, you have a bunch of faces that get formed. And if you pick one of those faces, then the degree of the face is 2 times the number of edges also. So what's the degree of a graph? Well, if you embed the graph, so let me just draw a planar graph in the simple plane, like this, let's say. So let's draw a face. So here's a face. The degree of the face is how many edges are contained in it. So the degree of the vertex is how many vertices are contained in the edge, whereas the degree of the face is how many edges are contained in the face. It's sort of like the dual version of this. So you have this one, you have this one, and you have this one. So then the degree would be 3. Okay? Now, so this is technically, so we're drawing it in the plane, but in actuality, it's embedded on the sphere. So when it's embedded in the sphere, you also have this region on the outside. So this would be a face. And for that face, you have a large degree number because all of these are the edges that are then contained. These would be the edges that are then contained in your face. So then the degree would be 1, 2, 3, 4. You would have 4. So this outside face would have degree equal to 4. So that's the way, it's the same exact idea. So here's how we prove. So let's give a classic proof. It's a very nice proof. So let us prove. So let's state this as a theorem because this is pretty surprising. And the theorem here is K5 does not embed into S2. However, it does embed into the torus, but you will show that K8 does not embed into the torus. It's almost the same kind of argument, you just have to tweak it a little bit. So proof. Now, of course, it is not sufficient to just start drawing pictures and then saying, I cannot figure out a way how to do it. Okay, so because sometimes you cannot figure out how to do it, but maybe there's a different way how to do it. Sometimes you cannot see it. That's actually what happened with the torus example. I was trying to embed the utilities graph on that torus picture, and it was not working out for me. So I had to switch to the rectangular representation of the torus, and then it was easier to then figure out. So just because you cannot see a way how to do it by just drawing edges does not mean there's a configuration that actually works. You can always say, well, maybe if you were clever enough, you would have figured it out. So you have to actually give a proof. If you try doing it for hours and hours and hours, and it does not seem to work, then probably it cannot be done. right? Probably, but that's a. And I'm thinking, so maybe this is like an interesting question to ask. Like, I do not know how to answer this question, but maybe some of you know. So as you know, a lot of times what we do is we put a math problem on a computer because we do not want to solve it ourselves. If it's like a problem that requires a lot of cases, a lot of brute force, a lot of different combinations, and we're kind of going through it, seeing if it works, we often put problems like that on the computer, and we just tell the computer, you check through all of the combinations. And then you leave the computer running for hours and hours, and it goes through millions and billions of combinations, so you do not have to do it yourself, and it sees if it can find something. So I'm thinking, how would one program a computer to try random paths on a torus, and seeing if you can find something that would avoid self-intersections, all of those paths, and will give you a proper embedding. So I'm kind of just thinking about how would you turn that into some kind of computer assignment so it can do that for you. But maybe some of you know that would be sort of an interesting thing to think about. Because obviously, in the old days, you would do this by hand, but nowadays, we would take advantage of a computer and save ourselves hours or possibly weeks of just trial and error. So here's the way the proof goes. We would assume, for the sake of contradiction, that K5, the notation that we often use is we kind of use this. So this is sort of like an inclusion. There's an inclusion into S2. It embeds into S2. Okay, so let V be equal to 5 choose 2, so that's 10, be the number of vertices, and E be equal to, okay, I messed it up. So E is 5 choose 2, that's the number of edges. And V is the number of vertices, This is, by the way, how you know you're doing more advanced mathematics, because E does not represent the number E from calculus. That's sort of beneath you now. Calculus is beneath you. It now represents something else. Sort of like pi represents the projection map or stuff like that. So that would be the number of edges. This is the number of vertices. And then by Euler's theorem, if F is the number of faces coming from the embedding, so F is not part of this graph. This could be an abstract graph, right? This is some topological space, but it embeds into S2, and then you can visualize it as a subspace of S2, and then you can actually see those faces get formed. And then you just count the faces that get formed. So if F is the number of faces, then V minus E plus F is equal to the Euler characteristic of S2, which in this case is 2. So vertices 5 minus edges 10 plus faces F has to be equal to 2. So what is F? F is therefore 7, right? So the number of faces need to be equal to 7. Okay, here's the next thing. If so maybe I'm not a fan of this notation. Let's use capital letters. You'll see why. E is the number of edges, V is the number of vertices, and F is the number of faces. Then V, E, F is 2, and so F is equal to 7. So it's equal to 7. Okay, so here's what we do next. So now we're going to label the faces as F1, F2, F7. So that was the reason why I used an uppercase letter. If I call that F and I call it F again, looks bad. It's not wrong, but it just looks bad. Like, why are you reusing the same letter? So I just made it uppercase. So uppercase letters is just the number, lowercase referring to the actual faces. So there's 7 of them. So let us label the faces. So it's F1 to F7. So those are the faces. And observe that each face is bounded by at least 3 edges. So why is this? This is because K5 has no loops and it is not a multigraph. So if you find this confusing, here's what you should understand. So if you have a loop like this, so this is a loop, and this is F, then the degree of F would be 1, because the degree of a face is the number of edges that are contained in the face. So that would just be 1. If you have a multigraph, so a multigraph is when you can have multiple edges between 2 different vertices, and this is F, so this is a multigraph, then here the degree of F is equal to 2, because you have one going like this and one going like this. So in our situation, there is no loop, okay? And you cannot reuse this. So you have to use something else. You're not allowed to use this. You're not allowed to use 2 of them. So there's another vertex somewhere else that bounds it. So it has to be at least 3. So in our situation, when you have your face, it has to have at least 3. It could have 4, right? You can have 4 or something. So here the degree would be 3. Here the degree would be 4. But you see that it's at the very minimum, it has to have 3. It cannot have 1 and it cannot have 2. It does not have 1 because there's no loops, and it does not have 2 because it's not a multigraph. By definition, right? By definition, so what's the definition of K5? I mean, you can draw a picture for K5. So as a picture for K5, you have 5 of them, and between any 2 vertices, you draw exactly 1 edge between any 2. You do not draw any loops or anything like that. You draw exactly 1 edge between any 2. So it's not a multigraph and there's no loops. So as a result, it means that every face is bounded by at least 3 edges. Okay, so as I said, this is a somewhat pictorial proof, but it's pretty convincing. Like, there's probably a way to make this more rigorous, but then you have to define what it means to be a face, then you have to define what it means bounded by a face. You have to kind of start defining those things, and then you have to show that the obvious pictures that you're getting is consistent with the definitions. And it's certainly not worth it to go there, because this is just an interesting topic that it nicely fits with everything that we've talked about, but we're not going to use it again. And I think people should at least see it because it's like a nice conclusion to the Euler characteristic. And it also shows you how graph theory intersects with topology. Graph theory is combinatorial, it's in computer science, it has all sorts of ways it appears, but it's nice to see that it also appears in topology as well. So technically what we're doing is called topological graph theory. So graph theory is a very large subject, and there's all sorts of things what people might do with graphs. In fact, another thing that people do with graphs is people do geometric group theory, and you often use graphs there as well. So there's all sorts of things that graphs are used for, and they're used a lot in computer science and so forth. And there's a lot of algorithms that people are interested in. You can pick up books on graph theory that are only discussing various algorithms that one does on a graph and how you implement them on a computer, and how the structure of the graph influences the type of algorithms and all that stuff. So some people are interested in that kind of stuff. Here we're just doing topological graph theory. So, okay, so there's at least 3 edges. So what happens next? So here's what happens next. So by the hand shaking lemma, the sum. So let me do it like this. The sum of over all faces, let's say I goes from 1 to 7. There's 7 faces, Fi, the degree of every face. So what is this equal to? So this is equal to 2 times the number of edges, 2e. So this is equal to, how many edges do we have? 10, so it's equal to 20. But at the same time, if you look at this sum, this is greater than or equal to I from 1 to 7, and we said the degree has to be at least 3. It has to be at least 3. So the degree of each of these is at least 3. So look at that. We're adding the number 3 7 times, so that's equal to 21. And now we see the contradiction. The sum over all of these is 20. So this is 20. So we have 20 is greater than or equal to 7. So this leads to a contradiction. And there you go. So you have obtained a contradiction. Okay, that's your contradiction. And it's a very nice argument. It's pretty convincing, actually. There's hardly any pictures, right? I mean, I guess we have to draw the definition of a face depends on the picture, but that's pretty, I mean, that's not too difficult to understand. So it's a very nice kind of a picture. It's a very simple proof, but because it's so simple does not mean it's easy to find. Like, this was like the crucial observation. This is by no means obvious why one would ever consider something like this. But you can see that if you do consider it, it leads to a contradiction. It's because 20 is not bigger than or equal to 21. And it's kind of interesting that this is like as tight as it can be. That's like the smallest as it can be that actually gives you a contradiction. Like if this number was 20 and you had 20 bigger than or equal to 20, there's no contradiction out of it. So this is like as close as it can get to giving you a contradiction. And you just have to modify this. So on the homework, I'll give you some variants of this. So you can do this with K8 does not embed into the torus. And you just have to slightly modify this and figure out how it goes. But that's the nice thing about this argument. It generalizes to many other types of problems as well. So this concludes our discussions about surfaces, classification of surfaces, triangulations, Euler characteristics, all of that. Very interesting topic. I think it's a highlight. It's a highlight of topology, and it is an insult to any topology course to take a topology class and never see anything like that. And the next thing that we will do is another somewhat interesting problem, and it's the problem of knot theory. This is when you're given knots and you want to be able to distinguish whether two knots are the same or different, and how you can use topology to figure that out. So that's going to be the next 2 topics that we're going to consider. Now, knot theory is a very large area of math that would be its own separate course. And usually the techniques that are used in knot theory do not require the material of this class. But we're only going to focus on that aspect of knot theory that uses the fundamental group. So usually people do not use the fundamental group. They do other things with it because working with the fundamental group is too difficult, so they do other things. But I do want to at least show you how one can use the fundamental group to distinguish between knots and also links. We'll say what a link is. So that's going to be the next discussion that we'll discuss when we meet again with our next lecture.